Good day, everyone. This is the second part of my presentation with the fundamentals of electronics 1. Well, in the previous video, I have discussed the fundamental theories and some characteristics applications also about diodes. Now, in this part, I will be discussing to you about resistors. Okay, so let's start. What you can see here in the picture, no, are resistors, specifically carbon resistors. They are well known with their cylindrical shape with some bulges in the ends and with some color stripes. Okay. Later we will realize what are these stripes for and what are their significance. Okay, so as you can see in this picture, you can see also the schematic symbol of a resistor. You know, this is the schematic symbol of a resistor. It has a straight line with some zigzags around, and then another straight line. So typically, this is the schematic symbol for resistors. Okay, so resistance is defined as the ability of a material to resist the flow of current. An electronic component capable of providing resistance as its primary purpose is called resistor. So as you can see in the pictures here, these are not hot dogs. Okay, these are resistors. No, there are huge ones, there are slender ones, there are short ones, and there are long ones. Okay, and they come in a variety of colors. No, a variety of colors, variety of sizes. So that's how diverse no the manufacturing of resistors in the field of electronics engineering and electrical engineering. Okay, so remember always that conductors have less resistance, insulators have very high resistance, and semiconductors have an intermediate level of resistance. Okay, so that's why for conductors, it would be very easy for the current no to flow into them because they have less resistance, while insulators have very high resistance, and there is that term, energy gap. They have high energy gap, and in order for conduction to happen within the material, the electrical potential should surpass the energy gap of insulators in order for current to flow. Oh, okay, so what's nice about semiconductors is that they have an intermediate level of resistance because, as we know, semiconductors have characteristics to similar to conductors and similar also to insulators. Okay, so what I'm presenting here are the schematic symbols for resistors. So I've presented this earlier, the symbol for the resistor, but this it's more like an elongated rectangle, is also a symbol for a resistor. Now they just differ in usually who are the authors of that book or of that reference you are um, looking at, because US authors usually use this symbol, and European authors usually use this symbol. Okay, so and sometimes when you look to other materials, they were interchanged, but typically they're the same. They're all talking about resistors. So we have the fixed value resistor, rheostat, potentiometer, uh, tap, thermistor, and photoresistor. So fixed value resistor has a fixed value also in terms of resistance. No, they may have a tolerance usually by 5%, 10%, or 20%. And we have this rheostat and potentiometer. They are under the family of variable resistors. What do you mean by variable resistors? Rheostat and potentiometer, their resistance levels can be altered. No, can be manually altered. No, like rheostat, the difference is that rheostat has two terminals, while potentiometer has three terminals. No, so if you can see in the schematic symbol, it's like a typical fixed value resistor, but there is a superimposed slant arrow signifying its variability. No, in the potentiometer, the third terminal okay, the third terminal visually is in the form of arrow. Again, a rheostat and potentiometer operates the same because they are variable resistors under the same family, but rheostat only has two terminals, while potentiometer have three terminals. Okay, so this is the symbol for a tap. resistor. And this is a thermistor, or what we mean with thermistor is thermal resistor. It is usually used in applications where heat is strategically manipulated or measured. We use the thermistor. Like for example, your air conditioner, it usually use thermistor, and other heating devices, they use thermistor as like a component to signify current flow to some situations or to some setup. So thermistor is usually used in those applications. And we have this photoresistor. Like what's special about these resistors is that they behave actually. Their resistance level changes based on the amount of light uh, coming into them. Like for example, if there is too much light, then there is lesser resistance. But um, if there is lesser light, then there is higher resistance, and vice versa, depending on how this photoresistor is connected in a circuit. Okay, so we have these different types of resistors. So earlier, you've seen that these are the schematic symbols, but when in the actual, these are their forms. No, these are the different types of resistors. And if you have like free time, or you can always do more research, like what are the actual pictures of these resistors. No, we have this potentiometer, like there's a knob to control its variable resistance, the carbon resistors, and all the special resistors. These are the resistors that we need to know. Okay, and typically they are very small. Some you can also adjust using a screwdriver to adjust the resistance, but usually the most commonly used are the carbon resistors and this potentiometer. No, like you use a knob to adjust the resistance. Okay, so what are the factors that can affect resistance? So we're gonna talk here some factors that we need to consider in order for us to know whether the resistance of a material is high or low in a given circuit or in a given circuit condition. So we have actually four letters for that. We have the letters M, A, L, and T, or MALT, an acronym for MALT. Okay, so there is difference in resistance when it comes to material. There is difference in resistance when it comes to area, specifically cross-sectional area. There's also difference in resistance when it comes to length. And there's also difference in resistance when it comes to temperature. So let's explore more about these mult factors that are affecting resistance. So let's start with material, no? As what they say, not all electronic materials have the same value or level of resistance. It depends on the material's composition and electrical characteristics. So for example, no, if the the level of resistance of a conductor is different to that of an insulator, and is also different to that of a semiconductor. Like for example, if you're in typical applications, like for example, you're going to use a wire, no? So if the other wire is a copper and the other wire is an aluminum wire, obviously these are different materials. So you cannot expect that they have the same level of resistance. One may be higher or one may be lower. So it is very inherent that different materials used in electrical and electronic circuits also exhibit different levels of resistance. Okay? So let us take note about that thing. Next is area, specifically cross-sectional area. So for example, you have the same material, the same the same length, but what if they differ in the cross-sectional area? No, so cross-sectional area usually involves a radius, a diameter. So imagine yourself like if you are the current and you are like a water flowing in a tube. So if the diameter of that tube is great or large, then I think it would be very easy for us to flow inside that tube because the cross-sectional area is large. But if the cross-sectional area is small or lesser, then that means the resistance is greater. And it would be very hard for us, assuming ourselves to be water flow, to enter that pipe. Okay, so I think that's the analogy of the concept of cross-sectional area when it comes to resistance. The greater the cross-sectional area, the lesser the resistance. And the lesser the cross-sectional area, the greater the resistance. Okay, so let's move. So how about the length? What if the cross-sectional area is the same, the material is the same, but they differ in length? So based on theory, the greater the length, the greater the resistance. And the lesser the length, the lesser the resistance. So it's directly proportional, no? Resistance is directly proportional to the length of the material that is being used as a resistor or as a resisting material. Okay? So that's for length. Take note about that thing. How about temperature? What does which among the two have higher resistance if they have the material is the same, if the length is the same and the cross-sectional area is the same, but they differ in temperature? So which has a higher resistance? Which has a lower resistance? So based on theory, the higher the temperature, the greater the resistance. And the lower the temperature, the lesser the resistance. So I think this is very true, no? If you can see some videos like sub-zero temperature in which there is a phenomenon called superconductivity, no? Where there is almost no resistance and current passing to any material having like a sub-zero temperature or temperature below 0 degrees have a better way of flowing rather than temperature on the higher values. Okay, so again, the higher the temperature, the greater the resistance. The lower the temperature, the lesser the resistance. Okay, so those are the four components we need to consider when we are speaking about resistance. We have this thing, no, called resistivity. It is also connected to the concept of resistance. But resistivity is often used when comparing the resistance levels of materials. So in metric units, the resistivity is measured in ohm centimeter or ohm meter. It is typically represented with the Greek letter rho, no? And typical resistivity values of semiconductors, since in electronics engineering we are dealing mostly with the semiconductors, the silicon and the germanium, the resistivity value for silicon is 50 times 10 to the 3 ohm centimeter, and for germanium is 50 ohm centimeter. No, so this is the illustration of how resistivity is how resistance involving resistivity is being calculated. You know, like for example, this is the cross-sectional area, the length. No, so this is the formula to get that. And again, this is resistivity. The unit for that is ohm centimeter. Okay, so what I'm presenting next are some resistivities of common metals and alloys because the construction of some mechanical, computer, electronic, or electrical applications, we usually use some materials that also has resistivities for themselves. And the material, we have this aluminum, it's 2.6. Again, the resistivity here is expressed in 10 to the negative 8 ohm meter. So for aluminum, it's 2.6. For brass, it's 6. Carbon is 350. Constantan, or an alloy composed of a mixture of 60% copper and 40% nickel, it's called constantan. And we have the 50 resistivity. For copper, it's 1.7. Manganene, or an alloy composed of 84% copper, 12% manganese, and 4% nickel, we have a resistivity of 44. And for nichrome, or nickel and chromium, it's 100. For silver, it's 1.5. And tungsten is 5.6. So I'm presenting here to you some resistivities of common metals and alloys. Okay. Typically, you are not expected to memorize the resistivity values of this, no? But maybe during your design phase in the near future, when you are going to deal with these common metals and alloys, and during simulation or mixing of ingredients, creating composites, prototyping, you might be oriented again with these resistivity values. Okay, so that might be useful in the near future. Okay, so again, it is these are some values of resistivities that we might encounter, no, during the designing part or simulation or experimenting part or the prototyping part of our engineering journey. Okay, so what can we see inside a resistor? So typically, these are resistors. I think you've seen this previously. No, but if you open that, you can see that you're expected to see a carbon here in this carbon cylinder, and then or a carbon film on a ceramic tube, or a nichrome wire inside. So there are varieties also of different variety of sizes and shapes, length, color, but there's also a variety of what's inside in each resistor. Okay, so interesting. Okay, so how to calculate resistance, no, or how to get the total resistance in any circuit. So typically, we only have two types of connection in a circuit. We have a series connection and we also have a parallel connection. So to get the total resistance of resistors connected in series, you simply have to add them. Like for this setup, R1 plus R2 plus RT, that's the equivalent resistance. Now for parallel, R1, R2, R3, if you want to get the total resistance of these three resistors connected in parallel, the equivalent resistance is that you add the reciprocals of R1, R2, and R3, and after adding that, you get again the reciprocal. So that is the total resistance calculation of parallel resistors. Okay? So you need to really familiarize yourself and know how to add resistors in series and how to add resistors in parallel. So these are the formulas. Okay, so we should equip ourselves with this basic knowledge, especially in resistance calculation. Okay, moving on. How to read a carbon resistor's value. Okay, now this is the time we're going to read um, carbon resistor's value. Okay, and this is a carbon resistor and we have these colorful strips. So we need to know now what are these strips so that we will be oriented how to read it visually and then use mathematics to calculate its value. Okay, proceeding. So this is we have a resistor color code. So some resistors have one, two, three, four strips. There are four band. There are also one, two, three, four, five strips or five band resistors, and there are also one, two, three, four, five, six band resistors. Okay, so these colors are representing different values. No, as you can see, this is the line for the first digit. This is the line for the second digit. This is the line for the third digit for the 5-band and 6-band color code. But for the 4-band resistor, this is the line for the multiplier. Okay? And the fourth band for the 5-band and or the fourth strip for the 5-band and 6-band resistor is counted as their multiplier. Okay? So the fourth strip for a 4-band resistor and the fifth strip of a 5-band resistor and the fifth strip of a 6-band resistor is counted as tolerance. And with the 6-band resistor, it has a special temperature coefficient band. Now, the mostly used resistors in the electronic circuits, electrical circuits, are usually the 4-band color code. Now, so how to read this one? Okay, so let's try to read this one. Um, this is color brown. So as you can see, the color brown represents value of 1. The second strip is black, and black is 0. So 1, 0. And the third band, the multiplier is orange, 1000. Okay. And the fourth band is gold. This one is gold. And as you can see, gold is plus minus 5%. So therefore, 10 times 1000, okay, plus minus 5%. So the value would be 10 kilo ohms. 10,000 ohms or 10 kilo ohms plus minus 5% tolerance. Okay, so that's how you read this 4-band resistor. Now with a 5-band resistor, as you can see in this picture, the first strip is yellow, and yellow is 4, and the purple is purple is 7, so 4, 7, and the third is green, so 5, so 4, 7, 5, and the multiplier is 100. So 475 times 100, okay, plus minus brown, 1%. So we have the value of 47.5 kilo ohms plus minus 1%. So that's how you read the 5-band color code resistor. For the 6-band color code, we have red. Red is 2. Purple is 7. 2, 7. Then blue is 6. So 2, 7, 6. And the multiplier is black. So 276 times 1. The tolerance is gold plus minus 5%. And the temperature coefficient of brown, which is 100 parts per million. So we have the value of 276 ohms plus minus 5%. So that is how you read resistor color code, no? Try to take note about the first digit, the second digit, the multiplier, and the tolerance, no? Specifically in the 4-band color code. For the 5-band color code, you need to know the first digit, second digit, third digit, multiplier, and the tolerance. Now for the 6-band color code, first digit, second digit, third digit, multiplier, tolerance, and the temperature coefficient. But again, as I'm saying earlier, what we usually use in electrical circuits is this 4-band color code, which only involves first digit, second digit, then multiplier, and then the tolerance. Okay, so I think we need to orient ourselves about this resistor color coding, and if possible, we need to memorize it, no? Because we will be encountering several number of resistors, especially if we are designing some circuits, no? During simulation, prototyping, troubleshooting, or when you suggest values of resistors if you design theoretical circuits. Okay, so what I'm presenting here to you is how to memorize, no, this resistor color coding. So we have from numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, where 0 is black, 1 brown, 2 is red, 3 is orange, 4 is yellow, 5 is green, 6 is blue, 7 is violet, 8 is gray, 9 is white. And then we have this plus minus 5% if the fourth band is gold, and plus minus 10% if the fourth band is silver. And if you don't see any band here, no band, it's plus minus 20% of the value. Okay, so you can actually memorize it, no? No need for an acronym or mnemonics about this. Okay, 1, 2, 3, go. I'll just memorize black, brown, red, orange, yellow, green, blue, violet, gray, and white. More like BBROY, GBVGW, then GSN. But I ca we can also suggest, no, like mnemonics in order for us to remember this lineup of colors. So why not remember this term, bad boys, rape our young girls, but virgins give what God say no. Again, it's just a funny or kind of catchy statement. Bad boys rape our young girls, but virgins give what God say no. So bad is black, brown is boys, red is rape, orange our, yellow young, girls green, blue but, violet virgins, gray give, white is what, and then the God say no thing is all about the tolerance. God is gold, say is silver, and no ban is no. Okay, so bad boys rape our young girls, but virgins give what God say no. So it's just a catchy statement. You might you might want to use this in order to remember better this lineup of colors. But if not, it's also okay. No, you can simply memorize black, brown, red, orange, yellow, green, blue, violet, great, white, and then gold, silver, no band. But if you are okay with this catchy statement, then you can also use it. Okay, so that's the word of resistor color coding, resistor calculations, the characteristics of resistance. We've talked also about resistivity. So again, as we know, resistance should be deeply studied, no? If we are designing electrical circuits and electronic circuits, because circuits involves currents, and currents needs to be controlled, whether it can be whether it should be amplified or minimized. Then the use and strategic use of resistors is a very good thing to design these circuits, depending on the application or the requirement of the application. Okay, so that's it for the resistance. I hope you've learned something, and this is my final slide. We find in life exactly what we put into it. So we are all upcoming engineers. We are all upcoming technicians. We are all upcoming designers. So exactly what we put in life, our effort, our enthusiasm, then these things might bring us to greater heights, especially in the world of innovation and making progress with our technology. And with that, we can amplify and help the people around us and make the world a better place and make life easier. Okay, so I hope you've learned something about diodes and resistors. And this is Engineer Logan Stampa. Thank you, and God bless us all.